it's really exciting to have Vikram visit us. Vikram is a professor at University of Washington and has done really exciting work that is so interdisciplinary. I don't even know what area you're in. It's a combination of like UV comp and HCI and electrical engineering. He just builds really awesome tools that are actually really helpful for the world, which is, something that, a lot of us aspire to do. And he's also spending a day a week at Amazon these days, so bringing a lot of, that kind of expertise into the mix. And yeah, so thank you for visiting us.
Yeah. Thanks for the intro, and thanks everyone for coming. So yeah, today I want to talk a little bit about the work that we've been doing on how to design more sustainable computer systems, and for a way to design or redesigning the electronics that power our digital world. Maybe before I get started, just feel free to interrupt, ask questions whenever, right? We can make this interactive. Like, I have a set of slides here, but if there's stuff that you're particularly interested in, then yeah, let me know. Happy to chat. But before I get into the details of the some of the projects that we've been doing, I wanted to give some background on what the environmental impact of electronics are and where that comes from. So if I can advance my slides. There we go. So we've got computers all around us, right? They power everything. I've got my laptop here. We've got, I have my smartphone in my pocket, right? And we also have all of these things. We have IoT devices everywhere. And these things all also connect to the cloud, where we also run our AI models now, right? And we've done over the past, some number of years, we've really done a good job of making these things relatively seamless to use, and this is kind of the vision of like ubiquitous computing, right? But and it might seem like the cloud, for example, is this abstraction where we have basically infinite compute, right? But we have to remember that this is, the cloud, for example, is, even though it's something that we don't think about every day as maybe like disappeared from our everyday use, it is a real place of a bunch of data centers, right, that are out there somewhere, and you've got racks of servers, all the cooling equipment, and it's really this giant building with a bunch of computers that takes a lot of resources to physically build and then also to run. And each of, there are many aspects of these physical devices that have direct environmental impacts. So what are these? We're used to hearing about, say, the power grids, right, and carbon emissions, but there's actually a lot more than that. And this is something that I like to emphasize when I give talks on sustainability, is that it's important to think about what environmental impact you are talking about, right? So again, there's carbon emissions that come from burning fossil fuels primarily. But then there's also, what happens when we throw out our electronics at the end of life, right? So these things end up in landfills, and those have impacts on, say, soil and groundwater, especially depending on how you dispose of them. We've also, of course, heard of microplastics, and that's kind of where that fits in terms of toxicity to humans and the environment. And then, another category that we have is things like land and water use, where, especially if you're building a data center in the desert, right? Then, it's taking up a lot of resources from that region. So the point of this is just for anyone that is thinking about, hopefully excited about working on these problems, to kind of think intentionally about which one of these you want to address. And or yeah, so to really have impact, you need to think about these metrics. Um, and so the other thing that I want to mention is, in this talk, I'm primarily going to focus on things like carbon emissions and this, things like e-waste that produce, human and ecotoxicity. But where did these things come from? Well, I said, you've got all these computers, right? But the environmental impact of these things comes from actually the whole life cycle of creating the physical device and using it. So at the beginning, you have the raw materials that it takes to say, there's the aluminum chassis of this laptop, right? That has to come from somewhere, as well as all the materials that go into making the chips that are in our devices. So that's kind of all of the raw materials in manufacturing. Then you have transportation of like getting it from point A to point B, all of the logistics involved in that. The use phase, where this is often where we talk about, power that our devices burn, and then end of life, which would be which would be when you throw it out, right? And you may hear, for example, in carbon emissions specifically, people like to talk about this as like scope 1, 2, and 3 emissions, where scope 1 is like you are directly burning some fossil fuel and emitting it in the air, right? So that might be you're driving your car, right? A scope 2 emission is something that's indirect. So all of the power that's used to, say, even to run an electric car, right, would be a scope 2 emission. And then scope 3 is everything else kind of upstream, right? And for most computing devices, we're really thinking about, scope 2 and 3 emissions because, the devices that we're making aren't actually emitting something into the air. We can look at this, for example, if we look at a specific example, something like a data center, and I'm picking this because it really includes all of these three, right? You have, everything that goes into building it is this, what we call embodied emissions, upstream. And then you have operation, like that use phase, right, of the power. But also there's a little segment there that actually produces direct emissions of, say, diesel generators that are used for backups, right? They're burning something, they're creating emissions. And then you have embodied downstream, which is, when you throw these things out. And let's say that waste process, how you treat the waste, has some emissions there. And similarly, you can pull out for doing the semiconductor fabrication that goes into building the electronics there, right? You have similar things and or this same breakdown. Here, though, the scope 1 emissions of the chemicals that you use in the fab in the clean room, right? Those actually have substantial impacts as well. So the reason that I'm sharing all this is just to give you hopefully a sense of, we talk about the environmental impact, carbon emissions and everything from computing. Where does all that come from? So, okay, I've told you, sounds like a lot of terrible things. Are there any ways that we can address this? And I want to share kind of two main themes that we've been working on. The first is sustainable materials. So we've been trying to create materials that can be either recycled or reused or that are biodegradable to actually create our electronics. And to back up for a second, there are a lot of people who are doing important work on reducing power, right? And that is, that's something that's very valuable, right? But I think there's a problem that less people are working on of those embodied or upstream emissions, right, that I talked about, that actually account for, say, 50% of what go, the impact of our devices. And that's kind of really what my group has been focusing on through sustainable materials, and then a lot of work with Adriana on design tools for fabrication. So here what we've done is we've created things like what you're seeing in this little video is a circuit board that's completely recyclable. What we can do is we can put it at the end of life in this solution where all of the it kind of swells up and all the materials in that come apart, and we can actually reuse them to make a completely new one. We've also used that same technique to create different kinds of cables and flexible materials. And we also have some work on creating biodegradable materials. What I want to focus the most of the talk today, though, on is on this other space of creating design tools for sustainability. And as I mentioned, this is all work in collaboration with Adriana. And what are we trying to do here? Well, broadly, one of the things that we've realized is that to really be able to enable people to reduce carbon emissions of electronics, right? we need design tools to empower people to do that, right? We have tools that, for making chips, making circuit boards, all of these things. Why can't we have tools that will help people prioritize carbon and other impacts? So that was our initial vision a couple of years ago. We're like, all right, we're going to create a design tool. We're going to create this, optimization things for that, right? And then we realized, wait a minute, we need to have some function to optimize over, right? Where do we actually get this data on, say, carbon from? And that's kind of what led us to this world of trying to do sustainability assessments to even get that information. Because it turns out that when you see the carbon footprint number on something, that actually takes a whole team of people to compute, and you'll see in a couple of slides why. So the first set of projects the first project that I'm going to talk about here is broadly on how we can automate that process of doing a sustainability assessment. How do you compute the carbon footprint of a physical thing, right? Second, I'll talk a little bit about how we can communicate that impact to people. For example, if you go to a web page, right? Can you analyze the content there and automatically tell someone a little bit about what the carbon footprint of something like shipping or a product that you're buying is, to give people a sense of how they can make more sustainable choices. And then the last is another design tool that I want to talk about, where in many of these cases we have imperfect or very limited information. Are there ways that we can inform design by doing things like making comparisons and saying, even if you don't know exactly like this thing produced X number of grams of carbon, can you at least reason about like, well, design choice A is better than design choice B, and kind of guide people along that path? So to start out, let's go into some more detail on this system that we've created recently on trying to automate the process of doing the sustainability assessment. So before we get into that, I want to explain how this process is typically done. At companies, and this is something that I've seen at Amazon in my part-time work with them. You have a whole team of people within the devices organization, right? So this is the part of Amazon that makes like Echo, Eero, all of those things, right? So you have engineering teams there, you have product managers, suppliers, this complex mix of people that all go into that do different parts of making this product, right? And all of these people also have key data that's necessary for computing carbon footprints. So what ends up happening is you have a team of people that are experts in what are called life cycle assessment, or LCA, and they're the ones that kind of gather all this information and then figure out how to compute the carbon. At a high level, what happens there is you first have to figure out all of the parts that go into a device, figure out the impact of each of those, and then you basically sum them all up. And one of the most challenging parts of that is collecting that data, as I said. If you look inside your phone, right, you have hundreds of different parts there in pretty much any electronic device that we have. What you're seeing here is an exploded view of a phone, right? And you have a breakdown of all the different little electronic parts there. You see here also, kind of zoomed in each of the little chips and also the resistors, capacitors, other components there. Within those, they also have all kinds of different materials, right? And so somehow we need to reason about all of this and figure out, well, what did it take to actually make one of those parts, right? And that gets even harder because nobody that runs a semiconductor fab wants to share any data with you. Well, that's not quite true. There is an ongoing effort by an industry consortium right now to try to create a data sharing platform, but there really isn't much. And you can think of for a lot of things in sustainability, there aren't incentives to share this data, right? So I think that's a key problem that needs to be addressed in this space. But to back up for us, those of us who are trying to do this this life cycle assessment, we need to first figure out what all of these parts are. Yeah, question.
Just to get a sense of like how things are, people who are LCA, people who are doing the LCA,
Yeah.
do they generally need to go to like the specific manufacturer that made it, or is there a big variance among manufacturers for a specific part?
Mhm.
Or maybe we don't even know because we don't have
Yeah.
a lot of numbers?
Yeah. That's a great question. And I think that really gets into kind of what why there's a large variance in the outputs that you'll get, even when experts try to do a life cycle assessment, right? And that depends on what data you have. There's some people where they will just do things based on industry averages because that's all you have, right? And so, for example, for something like steel or aluminum, there are kind of standard processes for making those raw materials, and you know what those are, right? Now, a specific company might have a supplier, right, that runs one of their factories on renewable energy. And so there suddenly the number goes down. And so if you're Amazon and you are, planning to, and I think already in many products they pay for carbon offsets to for the emissions that they do generate, then that translates to money, right? And so you do care about finding out whether that supplier has, the certificate saying that they run on renewables. But you're seeing there where that there is a lot of variance there, and I think that there are varying levels of quality at which and depth at which you can do your LCA.
Totally, yeah.
Yeah.
Yeah, that makes sense.
But I think you're also picking up on something interesting there that you'll see in a few slides of within the electronics industry, there are some things that we can do here of like looking at, say, clusters of how different parts are typically produced. So we go from, having a little bit of information about roughly how something is made to try to reason about what its impacts are. Yeah. Other questions? Okay. So, the way that this data collection is typically done is also is really done kind of at the end of the process. So you have your how do people actually make a device? Well, you're making prototypes, right? Product teams are doing that. Then that's an iteration loop of testing things. Then you actually go and manufacture them and then release them. It's usually at this point, once it's released, that and you have an idea of totally or the total list of things that goes into it. That's usually when people start trying to figure out like, okay, here's my list of parts. What is the carbon in it? And so the thing that you see here is this LCA computation is kind of this separate stream, right? That doesn't really feed into the design cycle, which means that there's no way that designers have to actually understand whether a choice that they're making is, more or less sustainable. And so what we'd like to do going forward is come up with a process more like this. And one thing that I want to mention is that these graphics are actually based on an interview study that some of our students did, where we talked to people at a bunch of different big tech companies, right? And have seen that pretty much everyone has processes that are kind of like this. And what we'd really like to do is move to a world where we can actually do continuous data collection across all steps of this pipeline, right? And so, the way that people came up with doing this process of LCA was really, from say like chemical engineering, where people had an industrial process and they were characterizing every step very precisely. But to be able to make certain design decisions, you may not need full information, right? What you might want to know is like, well, I'm creating a device that has a screen that's approximately this large. I know that it's going to have a battery, it's going to have XYZ, right? Can I use even that to start reasoning about what direction I should go with my design? Having something like this early on, even if it's not precise, can be very valuable to designers. So how do we get to this? Well, one thing that we've been working on is an automation pipeline for trying to do this, using a set of AI agents that kind of emulate the same process that you would have within a company with a bunch of experts. So, I mentioned how you'll have your product team, your sustainability expert, right? What we do here is we kind of emulate that, where we have this LCA agent that will query a stakeholder agent for a bunch of details. Maybe that's a bill of materials for a device. Maybe that bill of materials is incomplete, and then you kind of look up, you try to look up data on it, and you have this iteration loop. We also have a set of, if it'll show up on my slide, there we go. We do things to actually get this data. A lot of that, again, especially for us at universities, is proprietary and people don't want to share it, right? At a company that is different, that you have much more data available, but there's still gaps. And so what we've been doing here is trying to figure out how we can fill data gaps by looking at open online sources. For example, looking at teardowns on there's sources like iFixit where people post repair guides, right? That actually has a breakdown of all the different parts within your device. You also have things like the FCC database has for any electronic product that has a wireless transmitter, you actually have to submit pictures of the internals of your device on there. And so you have all of the different chips, or at least some idea of what's in there. So so we create these tools that the agents can run to retrieve this information. And then we so we do that. We also have a separate process by which we can, in some cases, look at knowing some kind of rough product specs, try to estimate what something is based on a distribution of carbon data that we do have. So we kind of combine these different methods to try to automate sustainability assessment. And I'll go into some more detail about how that works. So the first one is, how do we generate our inventory, right? Like the list of all the different things that we need to account for, every single resistor, every IC, right? One thing that we can do is, as I mentioned, repair websites like iFixit and the FCC actually have public data on all of the internals of devices, right? So suddenly there, what we can do is we can mine these images. We can identify, draw a little bounding box around a chip, identify what that is. Sometimes we can even read the part number on that, right? Or we can at least tell, like, okay, is this a small component like a resistor or capacitor that we have a reasonable model for, right? And we can estimate carbon for. Or is this at least like some kind of integrated circuit, right? And it turns out that actually one interesting thing is that if you just put these images into a language model, they do pretty poorly on extracting the information that we want. So what we ended up having to do is to create some custom tools that would kind of segment the image, right? Identify all of these components, and even for these long documents, say from the FCC that has like, I don't know, 20 plus pages of a PDF. How do we figure out the specific image that we want that actually has all of the chips? So so basically we created a system that does all of that. And the result is we can pull out information about what chips and parts are in a product.
Did you talk at all about what these custom vision tools are that do
Yep.
this?
Yeah. So the first one is actually very simple. So we want to be able to discriminate between the different images where, especially in the FCC database, you have, say, some of these pictures that the same part of the circuit board where some of them have the shielding on it, right? And that obscures what's under it. And so what we do is we find those similar images and we try to identify the ones we just take a Fourier transform of the image, find the ones that have the highest frequency content, because those are the ones that have actually, all of the details about the small chips on there. And then beyond that, what else do we do? We have, beyond that, we use kind of standard tools to be able to draw bounding boxes around these things. Identify, many of these images will have something like a ruler in that. And so you can use that to then back out what the size of that is. Yeah. Cool. Okay, so as you can see here, and what I'm trying to convey is we've gone from this problem of having zero information to we can actually start trying to reason about what's in these things. So how well does this work? Well, I've got some plots here, and I want to show a couple of examples of how close we get to so these two plots down here are specifically for say a GPU and a motherboard where we had public data available for them, right? And it turns out that we're actually able to get within 15 to 20% of the reported carbon footprint, which is actually on par with what an expert LCA typically is. And now you might be wondering, like, wait, 15 to 20%, that's good. The reason for this is actually because the way that these are done, right, is people make different modeling assumptions. So, there might be differences in data sources. There might be, again, differences in like which parts you consider and like what level of granularity and detail you go to. Do you use industry averages? Do you use your own data? And so those numbers alone can produce a pretty large variance within these reports. So, yeah.
I'm sorry, I missed something. When you say reported by who?
This is by the company that created it. Yeah. So and maybe the distinction here is that the tool that we developed has zero proprietary information. We're just looking at what's online, right? Looking at FCC public sources. Whereas, for example, at Amazon or I forget which company these two components are from. They have a team of people that has access to the primary data, right? And they're using that to do this.
Great. So that's great. You were able to build the connection to go and get that data, even though it's not public.
For these two for these two products, I actually have a public data sheet online,
Okay.
but we just use those as test cases,
Yeah.
right? Yeah. Cool. Okay. The other thing that we can do is I talked about visual data. The other thing that we can do is we can actually try to estimate this, some information about these things based on text features like text descriptions. You can think about like on a product page for a laptop, a phone, whatever it is, you have things like the screen size of a device, the processor that's in there, the amount of memory. And these all actually tell you a lot about the major specs and some of these big chips that actually contribute a lot to carbon. And the other interesting thing about those is that all of these things, like the highest end processors, are produced in a handful of semiconductor fabs, right? There aren't that many people in the world that can make these. And so we find that, and if you're trying to create a laptop that has XYZ components, there's only such a large distribution you can have in the carbon footprint values. Or this is something that we noticed as we started analyzing these. And so what we've done here is we basically come up with a bunch of features for particular products, right? And you can see that we basically, by taking this nearest neighbors approach of trying to match a product, with these features to the closest one in a known database of, public carbon footprints for, say, laptops, phones, the handful that are out there, right? We can actually, in some cases, get a fairly narrow distribution for the carbon footprint. And there we know that actually, if you've got a phone that's, with these specs, it's probably going to be within some range. I want to emphasize that this approach doesn't work for everything, right? It really depends on how much data you have for a particular class of devices. But it, again, is another way that we can go from having zero information to suddenly being able to reason about these things. And then, I've just got a couple of plots here that show a bunch of different experiments that we tried of looking at desktops and laptops and displays. Again, we have, as the size of your training set goes up, you have kind of more examples to compare against. With either 2 or 5 nearest neighbors that we're using, you can see that we're getting within this like 10 to 20% region. Um, the other thing that we did as part of this work was also trying to so a lot of what I've talked about here is, you have something like um, uh, like an entire product that you're trying to analyze. Before we were looking at the parts the individual parts, right? Trying to pick those out. The other key step of mapping parts to a carbon number is you have these things called emission factors, where you say like, X number of grams of steel or copper or whatever it is translates to Y amount of carbon, right? These are basically just unit conversions. And so there's sometimes you don't actually have these for certain types of materials. Or for example, for electricity in a particular place, what is the emission factor, right? It turns out we can use a similar process to also estimate these values as well. So we first tried this on electricity, where there is actually pretty good data available on how electricity is generated, their carbon intensity of electricity generation around the world. And so we tried this first here, and basically we took, all the data that we could find on the mix of like nuclear, wind, hydro, et cetera, dropped some of those, and then used that to test and see, how well can we predict these, right? Um, and uh, and again, as you have more and more data available within that data set, it gets pretty reasonable. And so what we really wanted to do here was see, well, can we use this for things like raw materials, new kinds of plastics, right? That you might use within a product. And by applying that same approach there, you can actually get within um, what like uh, 70 some odd percent of the value. Again, knowing nothing about actually measuring this process. And I think that there's a lot of room for improvement here of looking at like, the correct features to characterize a material that try to get you closer. And the other quick thing that I'll mention here is that this actually does better than the typical approach that human experts use. Of usually right now you tell an LCA expert, I have this plastic that's not in my data set. What do? Well, they pick the closest thing that is in that data set, right? And actually the detail I forgot to mention on the previous slide was we actually can uh, create a weighted average of, say, the 5 top nearest neighbors, right? And that actually, in many cases, ends up getting us closer to the actual value. So, um, so hopefully I've shown you here a little bit about how we can go from zero information about carbon footprint to actually reasoning about these things, getting some estimates. Next, I want to talk about some ways that we can actually communicate this environmental impact and create these interactive tools to show this information. And so the typical ways that that you have to analyze any sustainability for anything usually require all of this detailed primary data, right? You have to upload your BOM, whatever.
Sorry, what's a bomb?
A BOM is a bill of materials.
Materials.
Yeah, yeah. So that's like if you have a PCB, there are some tools where if you put that in, it'll try to give you an estimate. But what we wanted to do was, inspired by some work that on creating these interactive tools to analyze research papers, where you can basically change the values and understand kind of how this will affect something there. We wanted to create something similar for sustainability. And so, the first thing that we did here is we did a survey of, a few different ways or different strategies of trying to communicate this, for things like augmented text, where you can change something and it will automatically update a value, ways of visualizing parameters, coming up with equivalency. That turned out that this is actually something that was really useful to people. Like you just give someone a carbon number, right? And they're like, I don't really know what that means, but sometimes miles driven by a car is, is a good way to think about that. And then we incorporated all of these to create a system that will take in will take in, a natural language source like a website, right? Or research paper or something like that, process it and and try to give you a carbon number. And the other key thing that I want to mention here is that to enable this, we, under the hood, we create this data abstraction that we find is very helpful for taking, the raw information that you have of like you have material A, B, and C that you identify, right? And basically what we, in this case, we have an AI agent that tries to first match those to a particular life cycle phase, and then group them within this this data abstraction that we create that says, is this a material? Is this is this part of transportation? Is this the use phase? Does this relate to electricity? And then suddenly, once we have that, we can actually just run the LCA computation, right? We can go to a database, we can look up, well, okay, you have some number of grams of a material, you can multiply that by an emission factor, and then you can actually compute a carbon number from that. And so maybe I'll skip over this, but this is just some details on what that data abstraction looks like. Or actually one note that I want to add here, that something that we realized as we were talking in a group about creating these things is that a data abstraction like this, and eventually a domain-specific language, something that we're working on, one of the benefits to that is you can actually encode some of this this expert knowledge in in the way that you construct this, and make sure that it's valid to actually do your computation. Did I hear a question or?
No, it's just an interesting idea to be valid by construction.
Yeah.
Could you talk a bit more about that?
Yeah. So I think more broadly what we're thinking about there is, are you, for example, well maybe in this specific case, right? You have materials, right? And then you have each of the different life cycle phases, and there's only a certain way that you should do that computation, right?
But
You
to be physically conforming.
exactly, yeah. And so you can encode that in kind of in the way that you create either the representation or the language or whatever it is, right? To show that there are only certain valid operations that you can do. There might be, or you can also abstract this away if there are certain computation functions that you're allowed to do for certain materials, not for others, things like this. Yeah. Great question, though. Yeah, so how do we do compared to the state of the art? Well, on evaluations like shipping packages, where what we do there is we basically look at a website. You go to like FedEx or something, and you pull out the source and destination, and then we go behind the scenes and we basically take like the Google Maps API and figure out distance that it has to go for by air versus by land, right? And we get within about 10% of the actual estimate there. And similarly, for what we did was we actually analyzed a research paper, one of our own papers, right, where we created a custom material, and we had the chemical formulas and things, and we're also in different categories. The main difference ended up being in this raw materials section, but many of the others we were able to get pretty close to the actual numbers. So what does this look like in practice? Actually, I think I have a demo here that I can, or a video of a demo. I don't have the live one running on my computer. Students have that. But the idea is you could go to a research paper like this, you highlight a section. This is kind of the methods part of the paper, right? You click on that and you get this little pop-up, and it shows you, the total emissions, the equivalence of that, and a breakdown of where each of those came from. The other thing that you can do that I believe this will show next is you can say, well, what if I increase some of the numbers here, right? I put in more of a particular material, right? Then how does that change the mix? You can either preserve the the ratios between those, or you can put in like absolute numbers, and this adjusts in real time to show you that. And this is maybe one example of the types of tools that we would really like to create, so that people, as they are creating something, right, can actually reason about their choices and how this affects sustainability. And here you're seeing the demo for shipping. Yeah, and there you go. It pops up there and it shows you, well, if you're going by ground, all the way across the country, this is a route that would take, and what that would carbon that would take. Now, the other thing that I should mention here is you show this to kind of to specific LCA people, right? And they might have some issues with that, of like they're used to trying to do a very precise calculation of a very specific scenario, and they have a lot of data. We're coming at this from the other perspective of, let's say that you have very limited data. How can you get some estimate? Yeah, and you're seeing here, trying to train a model on this NVIDIA GPU, how much does that take? So, yeah, question.
So, sir, how do you get the carbon information for the FedEx page again?
Yeah, good question. So I think if you go back, let me see if I can back up in this video. So on this page, it'll tell you, you can parse the page and get the source and destination, right? And then really all we're doing is, I'm pretty sure we were using the Google Maps API, and just checking like from this place to this place, right? What is the distance that a truck would have to travel, right? And then based on that, you can estimate the amount of fuel, right, that it would take for for a truck to go from point A to point B. For things like this, there are actually pretty good industry average models online of like what ground shipping is like, and so we
What I'm
basically
curious about is that
those.
all these options are from the same A to the same B.
Yeah.
Right. So why is the last two options highlighted and like the most eco-friendly?
Yeah, good question. So I think so these two are ground. I think the others are air shipping methods. And so there, if it's on a plane, obviously it's going to get there a lot faster, right? But you're burning more carbon to do that.
I also have to ask,
Yeah.
the fact that it says 6 miles driven by a car is the equivalent, and obviously that's much farther than 6 miles. So is this something where it's like taking into account the size of the package, the
Yeah.
occupancy of the truck, and like dividing that amongst the things that
Yeah.
it's carrying?
Yeah.
Okay.
Yeah, good question there. So this is well, actually what this is breaking down is the amount of emissions, right? And yeah, of for for this this amount of material, and what does that translate to?
Yeah.
Yeah. Yeah, great questions. Okay, how are we doing on time? Actually, maybe I'll
10 more minutes.
yeah, so maybe I'll just so here, again, we made this tool. Maybe I'll just quickly mention, this last project where another thing that we've been thinking about is how do we do comparisons, or sorry, how can we enable people to reason about design decisions in, with very limited or imperfect data. And I just want to quickly highlight here that one of the things that we can do is, if we have a breakdown of all of the parts within a device, we can do these comparisons, right? Of like, is part A better, better or worse than part B, right? And this is a way that you can create a design tool that again helps people reason about decisions with very limited information. And And combining these things, one of the ideas that we're working towards is can we create a domain specific language that will will help with this process, right? To again encode like certain valid assumptions that we can make about a life cycle assessment, about different types of data sources that we have, moving towards a world where, the way that we write all other software, right, is we have these abstractions, right, that allow people to work at different layers of the stack of designing computer systems. Can we do the same for LCA, where, there might be people that are modeling a particular device, and then others that are trying to do the aggregate computation. Can you basically switch out data sources easily, right, and not have to redo the analysis? Ways to enable that. So maybe I will end there and open it up for questions, and mention that this is something that we are actively, something that Felix is working on like right now. But yeah, open to ideas, questions.
Thank you. Very pragmatic question.
Yes.
The demo that you were showing before.
Yeah.
Is this available to like anyone as a browser extension or anything? Like, is it this would be I'd love to play with that. So
Yeah. So the code for that is online.
Yeah.
I can share the GitHub link. I don't think it's like up there as a as like a a Chrome extension that you can just download, but you can build it yourself.
Okay.
Yeah.
Fun.
Okay, so I
Question.
have an interesting.
Yeah.
I have a thing that might interest you.
Yeah.
When you highlight the, GPU experiment.
Yeah.
This year at the Computer Vision and Pattern Recognition Conference, which just had its deadline.
Yeah.
Which has 35,000 people submit to it. We were asked to fill in a form.
Of how much
Of
time?
How much compute,
Yeah.
how much time and what resources we were using.
Yeah.
And everybody got so mad.
Yes.
that they had to fill in this form, a mandatory form. Part of the reason is that it was seen as like busy work, right?
Yeah.
And that this could be super interesting.
Mhm.
But the other reason, just to be able to do like a community level analysis.
Yeah.
The other reason is that nobody actually reports
Mhm.
accurately what resources they use.
Yeah.
Within the paper itself. They will only report partially the set of results. Right?
And well, that I feel like that's an issue that you have in all research communities,
Yeah.
right? Of
Yeah.
like, you only see the thing that worked, you don't see all the failed experiments before. Yeah. That's especially fun if you see any robotics videos. What you don't see is
Yeah,
all
all
the
the
tape
failed
that,
ones,
that
yeah.
got left out of that. Yeah.
So
Yeah.
I guess to draw that to its conclusion, I know it seems like a big ask, but is there a way to like estimate the gap?
Oh yeah. That's a really good question. And I think there are different ways that you can do this. There's one is you can come at it from the perspective, or one approach that some people will use is just looking at the amount of money that was spent on a particular thing, right? And if you have a breakdown of like, this is your compute cost, right? If you can get that invoice, then you know how many hours of whatever you paid for, right? And you can actually, from that, you can get pretty good numbers. I think for cloud compute, it's actually a little bit easier because most companies have a carbon calculator tool, right? And there's this whole other thing there of like, how do you attribute, the like the exact job that was running on this machine that's maybe doing a bunch of other things to, a specific amount of carbon. But there are tools that will do that. And so that's maybe an approach to
So
do
if I
this.
paraphrase, we're saying that the point of analysis is wrong. And then
Well, I think it depends. If you can trust the people that are reporting it, right? Then what you can do is you can actually do it at that point, right? Like, if you say, okay, every experiment that I run, I'm gonna log that, right? Then great. The other approach is if you can't do that or you don't trust, what people are doing, then maybe you go upstream.
thank you.
Yeah.
Would be more than like a multiplier than a gap. for
Exactly, yeah,
The incentives to perform lower.
yeah,
I guess sort of related to like community stuff, I think like the hard part is getting some of these like teardowns for electronics.
yeah.
And I was thinking like a lot of times like everyone has like hundreds of electronics at home.
Mhm.
And one thing I always want to do is like figure out what part broke in like the
Yes.
electric toothbrush or the Nespresso
Yeah.
whatever or the Roomba before I throw it away.
Yeah.
It feels so wasteful. So I wonder
Yep.
if you could just inspire the community a little bit to like, hey, before you throw away your Nespresso, take a like here's
Yeah.
how like take it apart. Like here's you have a heat gun or a little mini
Mhm.
screwdriver, take it
Yep.
apart and take a picture, and you could create like the Wikipedia
Yep.
of these
Yeah.
teardowns.
Oh, that's for like actually creating the teardowns.
Yeah.
Yeah, so that's a great idea. This reminds me a little bit though of were you gonna say something?
No, I was just, I think, no, I was just gonna point to Felix, so he he's thought of things related to
Oh,
that.
yeah, yeah. This also reminds me a little bit of some work from Pedro Lopez at Chicago. So he and his group that built this tool where they I think what they did there was if you have a set of designs of like parts, especially for those of us who are building stuff, prototyping in the lab, can you figure out what parts are in different devices so that you can reuse them, right? So you have this set of this library of parts that's like you could order them, but you actually already have them in stock here, which is actually, you might think of this as like only for hobbyists, but especially a few years ago when there were shortages of a lot of chips, right? That was a real thing that big companies were doing. They were buying things and taking them apart because that was the only way they could get certain chips. And
And people have been doing things like buying PlayStations to do compute and
Exactly,
so
yeah.
the repurposing of
Yeah,
parts has been
yeah.
a thing for a
Yeah.
while.
The repurposing things like PlayStations, there's another cool work from UCSD by Pat Panuto and some others there where they took a bunch of old smartphones and created a server with like I think like 100 phones or something. They put them all together and then had some software that would like make sure that it's distributing the computer across these like fairly limited things in a way that's useful. Yeah. Yeah. Question. Yeah.
In the beginning, you talked about here these three different aspects: carbon emissions,
Yeah.
and electricity,
Mhm.
land and water use.
Yeah.
And at the same time, you have Goodhart's law, which is like saying when a measure becomes a target, it seems to be a good measure.
Yes.
Basically, saying that we are playing a whack-a-mole game where
Mhm.
problem disappears at one place, but reappears at another.
Yeah.
And so, and also we know that
Is there a trade-off?
yeah,
Yeah.
during the last 2 decades, operational carbon has been going down, but embodied carbon went up for electronic devices. Right?
Yes.
So I guess my question is like, if we get embodied carbon emissions down for these devices, where will the next problem appear?
Yeah.
Is
Yeah.
because we can't, because it is under the same level of target complexity for
Yeah.
devices. Well, we can't really reduce anything and just shift around.
Yeah,
Because-
that's a really good question. I think there's a lot to unpack there, right? So I think one thing that you've seen there of why why operational and use phase emissions have gone down, right? Is especially in places like data centers, there's been a lot of that actually translates to economic cost too, of like your, less power, less money that you're paying for that, right? And so, there's you can kind of make things more efficient. And that's part of the reason why, and that was kind of an easy problem for a lot of people to work on of like especially within the CS community of like, okay, make your code more efficient, whatever, less power. Those things all kind of translate. I think the reason why embodied emissions are interesting and kind of the next thing to go after is it's that is something that's very hard to decarbonize, right? And where does the carbon actually come from in that case? Well, it depends a little bit. In some case, if it's a material that you have raw inputs going into and you're using chemicals that actually produce some gas, there are impacts from that. But then the other is actually just how many of these factories are actually running on renewables, right? That's actually one thing that Amazon is trying to do of basically getting suppliers to switch to renewables, right, to decarbonize. So that's kind of that's why there is still this big chunk of emissions there. And and what we really need to address. I think the other part of that is there a trade-off maybe to doing, focusing on one versus the other? I think that the one of the challenges there, or I think that there are creative games that people can play in terms of how they do their carbon accounting, and that's like I will count this for myself, but not others. But there's a growing number of kind of open standards for doing this, and at least within, like there's a GHG protocol, right? And people can take issue with this, but at least people are starting to speak the same language there, and that's actually a place where tools like this can help standardize that. I think that there are relations between, say, carbon and toxicity, water, land use, other things. But those are pretty complicated, right? Because you think of where that comes from, right? You might be able to reduce carbon in some way that may, or let's say for electricity generation, that might require more water, right? And so that's, I think that's kind of a tricky thing to think about. And I don't know that there's a straightforward relationship there. Does that hopefully answer
Yeah.
most of that?
And also we can just talk about
Yeah. So.
We wrap it up?
Yeah, thanks.
Okay.
Thanks again for coming.
Yeah. The other thing, last note that I'll end on is hopefully this inspired you to think that there are things that you can do in this space as computer scientists. So yeah.
Questions?
nice.
Yeah.